Uh, it's actually, this is day 5 of the lockdown here in Lagos. For some other people in Ogun State and Abuja here in Nigeria. So, but it's good that we still have this platform to still continue our learning. This is actually our second class on Zoom, and I hope we make very good use of it. So today we'll be working with today we're working with graphs and network processing. Now, networks versus graphs. I'll just try to run over this. When we're talking about networks and graphs, it's important that we understand their application in the real world. I think one of the ways I learn best with respect to things concerning data science is try to see, okay, where in the real world is this part of data science applied? It helps me to visualize what it is I'm working with, and it makes it easier for me. When we're talking about graphs and networks, it's important we understand that what we're basically dealing with is let's take for example Google Maps. Google Maps is basically something, a map of a community, of a state, of a city. Basically tells you all the networks of roads and how you can get from one place to the other. And obviously, to get from one place to the other, you can follow different routes. So you could look at it this way. When we're dealing with networks and graphs, we deal with things we call nodes, and then we deal with edges. Just take it this way. Let's say you're trying to get from where you live to, let's say you're trying to get to Awolowo Road in Ikoyi. What you have there is every street or every road you're going to take between where you are to where you're going to could be looked at as edges, while the beginning and end of those streets could be looked at as nodes. In your own present location will be looked at as a node. Your final destination will be looked at as a node. But every street you go through will be looked at as an edge, while the beginning and the end are nodes also. Now, what we have is a link or a road. We more or less, in normal discussions, you know that what we have is a road network. We talk about the road network, Lagos road network, how you can get to any and everywhere in Lagos, for example. So those are practical applications of networks and graphs. In this particular course today, we'll also be introduced to something we've not really talked so much about in the course of the course, which is algorithms. Algorithms are basically ways of solving problems. Particularly, this course will be focusing on three algorithms. Some of them, the application of which is widely used. There are things we use: Facebook, like I said, Google Maps. Then also ordinary how does Google rank pages and stuff like that. Those are the applications of these algorithms we'll be looking at today. Now, this what you can see on your screen now is a simple graph made up of, okay, you could say they are vertices or nodes. I prefer to use nodes because it's easy for me to visualize in my head, and edges. So you have a situation whereby you have 6 different nodes here, which is A, B, C, D, E, and F. Then the edges, we have one edge between A and C. Let's look at it this way. Let's just say that between A and C is a street. Let's say this is Awolowo Road, for example. But Awolowo Road starts from somewhere and ends somewhere. So this is basically a representation of what we are talking about here. So you could say, how do I get, what is the fastest route, or what is the shortest route to get from A to E or A to F, and as the case may be. So if you see the representation below, you see that we have the vertices, a V, representing all the nodes we have, which are A, B, C, D, E, and F. While we have a tuple of, I would say this is a set, not a dictionary. It's a tuple, it's a set, tuples of, within a set. Now, representing the edges, that is E. So you see that A to B is one tuple, that's the edge between A and B. So those are the basic representation of the different components of a graph model. Now, we can also look at things like, these are different characteristics of graphs. So we could talk about directed and undirected graphs. Now, in this context, you could look at it this way. If you are going from one point to the other, that is a direction. It means that you're going from A to B. But certain relationships that work in a network don't necessarily have a direction. For example, the relationship you have between you and your friends, let's say on social network, let's say Facebook, for example, the friends you have, there might be no direction between the link you have with your friends. What is apparent is that you are friends with A, you are friends with B, but there's no seeming direction per se. So that's a typical example of an undirected graph. But if you're talking about moving from one location to the other, there's some kind of direction in that you want to probably go from A to B. So the connection takes you from one place to another. So that's a typical example of a directed. And you need to also understand that just as you're going from A to B, you could also go from B to A. But if you wanted to represent it, you probably need to also draw, because you can see the arrows showing the direction. This is actually the direction from A to B. You have the direction from C to A. But if this, for example, if you're working with a road network, for example, the direction, it could be both ways, except in the situation whereby the road is something we call one way, where you can only go in one direction. But if it's a road where you can go in both directions, you probably need to draw a different graph to represent the opposite direction. But in this case, you're just dealing with something in one direction. Then we have weighted versus unweighted graphs. The same way we talk about using road networks, for example, every road, every edge, as we look at them in graph, will not have the same magnitude, because if you are going from one direction, from one place to the other, every street you enter will not have the same length, the same distance. So the edges can be weighted, in that the weight could be distance. But if you look at the context of maybe a Google map, for example, when they show you the shortest route that goes from one place to the other, the shortest route might not have the shortest distance, because other weights have been added to it, such like, okay, for example, how much traffic you have along certain roads might make up something that will be a weight in some way. But just look at it plainly that we are looking at distance as a weight. But in some cases, like I said, in friendship on social network, there may, although in certain instances, even when dealing with social network, there could be weights. But just between you and your friend, the people you're connected to, your friends, there may be no weight. In fact, there's no weight between you and your friend, except when being used in certain contexts. For example, there could be weight in something like, let's say on Twitter, for example, a celebrity that has millions of people following them. Their connection to all these, their followers, their followers to a certain extent have levels of importance. They might be just ordinary citizens, but even that celebrity might have other celebrity following them. In that case, there's some weight to the relationship between such users and their followers. But in the normal context of social media, we are really dealing with a graph without weights. Now, these are some examples of graphs in usage. This first one basically is the road network in, I think, Pennsylvania and stuff like that. So there are different representation of graphs that have been used in other research done all over the world. Now, in representing graphs, there are different ways we could do that. And in this particular course, we'll be looking at three different ways: adjacency, list, adjacency.
Hello, IK, are you still there? I think IK is gone.
Hello? Can you hear me?
Yeah, we can hear you. Can hear you.
Sorry, I'm actually using my phone as a hotspot, and a call came in, and I got disconnected. Sorry about that. Now, what I was trying to, okay, let me share my screen again. What I was trying to say is, in this case, we are trying to look at what are the other nodes that are connected to a particular node. If you look at the table on the right, you would notice that we have a list of all the nodes, and then we are trying to look at what nodes does that particular node connect to. Now, what we're trying to do there is this, is simple. You would notice that our node A is connected only to B. And so B is put in a list as being the node that is connected to B. In that case, what you have is A to B. From the edge, basically, is A to B. But you put it that A, for A, what it connects to is B. So in that case, what you have is A to B as the edge. In the case of B, B only connects to C, while C connects to A and D. So we have CA, and we also have CD being edges. But D is not connected to any node. So the list for its own edges is 0. So it has an empty list. I wouldn't want to go too much into things like the pros and cons, because in this particular instance, I wanted us to look at this thing from the perspective of being able to visualize it so that you can better understand what we are talking about. Because if I start talking about the pros and the cons, we might deviate a little bit, because the pros and the cons has to do with the implementation, especially when you're coding. Because if you're using a list to represent moving from one area, represent the edges, there are some issues with it, especially when it comes to removing particular edges. But because of the characteristics of list, obviously you would understand this if you have very recently I was reading a book about algorithms and data structure. When you try to understand the characteristics of lists and hash tables and stuff like that, you get to understand what the pros and cons are about. But just have it in mind that you could represent this as a list. But I personally think that when you get into more advanced cases, representing it as a list might become a major challenge. But like the disadvantage is the fact that removing a particular edge from the list deleting it becomes a major issue because of the characteristics of a list, obviously. Now, when we're dealing with adjacency dictionaries, in this case, what we're trying to do here is, now, this particular graph we're looking at here is, they have equal weight, in that we are saying that the edge between A and B is 1, between B and C is 1, and between C and A is 1, between C and D is 1. So what we basically have is a situation whereby we represent what the edge is and also the weight. So what we are basically having here now is a better representation in that we will look at it as a better way of representing what we did earlier, in that we don't just represent the edges. In this case, if you look at the first row in this table, we have said, okay, that we have an edge between A and B, and we have said that the magnitude of the weight is 1. If it was a weighted graph, for example, we can also just represent the weight as whatever it is here. So we're more or less doing the same thing with what we did with the list, only that we can add additional information here. But if we wanted to do the same thing with the list, we would have to have multiple lists, in that we'll have the list that holds what it connects to. For example, when we are dealing with this, we'll have a list that connects between A and B. We are saying, okay, the edge is B in a list. That means A connects to B. Then we also have that connection also. We have another list that represents the magnitude. So we'll need a list of lists to represent that, but we can easily represent it in a dictionary. Okay. Now, but this is actually even better, because you can easily represent it and say, okay, from A to B, in this case, we are dealing with adjacency metrics. You can say that from A to A, obviously, there's nothing between A to A, so obviously it will be 0. Between A and B, it will be 1. Between A and C, there's no connection, that's 0. And we are able to fill all these metrics, so we have a square metric. So this is what we eventually get. So those are the 3 different representation of a graph that we are dealing with in this particular course.
Sorry, okay. Someone is raising up hand.
Okay, hold on, please. Let me find out. Go, please kindly unmute the person so that the person can ask the question.
Okay, I'm seeing I'm seeing the matrix, the adjacency matrix, but okay. I thought from C to D would be 2. So why is it 1 and 0?
Please take your question again, please.
You know, from C we have 2 arrows pointing to A and to D. So, like can you please explain the matrix?
Okay.
From C to A something.
Okay, you were thinking that you have 2.
Yes, like from C to D. Okay. So I'm sorry. I think I understand it. I was trying to understand the matrix. I understand it now. I was thinking, because 2 arrows are coming out from C. I thought the matrix was supposed to be 2, but I just noticed that C to A is 1 and C to D is 1. Thank you. Sorry, I get it now.
Okay.
I don't know if you got what I was trying to say.
So what is basically, yes, I get what you were trying to say.
Okay.
For example, if you look at C now, you would notice that 2 arrows are popping out of C, which connects to A and to D. And if you look at the matrix, if you look at the column, the from column, if you look at the from, you see that C has 2 1s, which is the representation of how C connects to A is 1, how C connects to D is 1. So that has really been, but I understand what you were trying to get at. If anyone has any, if there's someone else who has a question, please go ahead and ask, but we'll continue. Now, there are 3 basic algorithms that we are working with. Oftentimes, when you start out, it's not every time when you start out in data science that you'll be introduced to algorithms this fast, because algorithms are usually things that you see, especially in the computer science world. But my basic understanding of it is that there are ways, algorithms are ways by which we solve problems. For example, there are 3 basic questions we are trying to answer here. Okay, how do we find the shortest path in a graph? That's the question you can ask. How do I find the shortest route from here, from where you are to maybe Banana Island? That's the question you're basically asking. So if you are using a Google Map, for example, if all Google Map considers is distance, if all it considers is distance, so if you ask the question, so distance is the only weight you are considering in that case. So you are saying, okay, what is the shortest route from where you are to, let's say, Banana Island? That's what, I'm not exactly sure how you pronounce this name, but I call it Dijkstra algorithm. Basically helps us to find the shortest route from one node to another. Now, the second algorithm we'll be looking at is the PageRank. Now, the PageRank, from what I understand, is one of the ways, one of the things that was the bedrock or the foundation of Google as a search engine that made it so successful, at least at the beginning. I think from what I understand, PageRank came as a result of the research that Larry Page and his colleague were doing. I think when, as part of their research, I think at Stanford, before they actually went ahead to start the company Google. Obviously, there are other things that came into play, but this is one of the ways by which Google was able to rank web pages better than previously done, because previously the ways of ranking, for example, when you go and you type a word on a search engine and you say you wanted to find pages that had, because when you ask a question on, let's say you're looking for data science. Now, ordinarily, what had been done previously was to find to find pages that had more representation of the word data science in quotes. So, but the reality of it, the page that has the highest representation of the word data science might not be the most important page for the word data science. Now, so the question of importance became a particularly interesting thing that needed to be considered, because just having the keywords alone doesn't mean that you have the right information based on the fact that there are millions of pages on the web. So they were able to find a way whereby they could rank pages not just by having those keywords, but by having links. If pages are linked to, okay, I'll better understand that, explain that as we go further. Let me just keep scrolling down. While the Girvan-Newman algorithm basically helps us to find communities, you could look at them. A community is basically let's say on social media, a group of people who they are interlinked with each other, but they are not necessarily as linked with other people. An example could be, let's say, those of us in this class, for example, let's say there was a social media for all the people who were learning data science. You would know that it is likely that everybody from AI Saturday Lagos, especially in this cohort, will be most likely connected with each other if such a platform existed. But also, yes, some of us will have connections to others outside of our own AI Saturday because we have other affiliations. But you would find a situation where those affiliations will be fewer and we'll have more affiliations within people within that particular group. So what this algorithm tries to do is to find all those communities. You could look at it in some way as some kind of segmentation if you want to look at it like that. So that's it for these three algorithms. So the first one we'll be dealing with is Dijkstra's algorithm, which basically finds the shortest route within a node. As you can see in this diagram here, this image, you could easily see that the black line, ticking line, shows you like the shortest route. This shows you the shortest route. So what you have here is, how do you find this? Ordinarily, if you're looking at it in an image, you could easily use your eye to eyeball it and say, oh, because of how you have to go in this direction, this is easily the fastest route. But let's look at it in the real world as if you were to go from, say, Oshodi to, say, DI, there are different routes you could take. You could go through Third Mainland Bridge, you could go through Ikorodu Road, or you could easily even turn back and go and pass a totally different route. And you could, at the end of the day, you could pass Kata Bridge, Third Mainland Bridge, or any other of the bridges, or you could choose to go through Ikorodu and then come by boat. So there are different ways you could do that, but because we are talking about things on optimal, you're looking for an optimal solution. You are looking for the fastest way to get to where you're going to. Now, but you also have to consider, okay, the weights. Are you dealing with a weighted system or an unweighted system? Obviously, in an unweighted system, you could say that each edge is just one. It's just one. So what you are looking at is you are looking at, in that case, you're just looking at fewer nodes. Which system gives you a situation whereby you go through fewer nodes to get to the final destination in an unweighted system. Then you also have a directed and versus an undirected. Does this connect to this? Does this connect to this? Those are considerations. Those considerations come into play. Then also you could talk about negative weights. Although when we're talking about, okay, for example, you could even look at this negative weight in terms of, if you're looking at Google Maps, for example, now, negative weights could be like traffic. You could look at negative weight as traffic, whereby you put a negative weight on a particular edge if there is high density of traffic at this particular point. So you could look at it from that point of view. Now, as much as possible on this platform, I try not to go into because when we go into the maths part of it, it becomes a bit difficult to explain. But here's the thing. Let me try and find a simple, okay, something like this. Now, you have A, B, C nodes. What we are trying to do here is, okay, we're trying to find how do we get from A to, for example, D. What is the shortest route? Now, how the algorithm basically works is this. Your starting point is A, so that's our source. Now, you now have an instance whereby because at the beginning, our source is A, you give it 0 because A, there's no connection between A and A, so we give it 0. But you don't know the distance between A and B, you don't know the distance between A, B, C, and the likes. You don't know, so you tag them as infinity. So that's what we have initially here. So you have between A and A, you have 0. Between A and B, you have infinity. Between A and C, you have infinity. Between A and D, you have infinity. But remember, what we are dealing with here is there's no direction. In this particular instance we're dealing with, there's no direction. So A is connected to B and A is connected to C. So when we initiate the algorithm, we find that we go from so we remove, since we've done this for A, so A has been established as being the connection between A and all the different nodes. We've established that, then we pop A. That means we don't go back to A. Now, what we do next is we now go to B, which is what we do in the second step. We go to B and we look at, from B to B is 0. But there's, hold on. But there's a connection between B and C. There's a connection between B and A. So what we have is 1, 1. Because remember, they are unweighted, so everyone has 1. But because there's no connection between B and D, that will still remain infinity. That will still remain infinity. Now, what we have been able to establish is that in this case now, we have that from A, at the second step, we've been able to establish that from A to B is 1. And we've been able to also establish that from B to C is 1. But from B to D is infinity. Then what we do is that we pop B. We don't use B any longer. We now go to C. We now have an instance. What we now have is basically that from C, so we have 0, 1, 1 between C. But what we still have is that between C and between B, we'll be able to do B and C. So for you to get from A to C, we've already established that the shortest path, now that's something that I didn't even make mention of, especially after the first step. Remember, what we had was 0, 1, 1 and infinity. What that simply means is that from A to B is 1, from B to C is 1, and from B to D, A to D is actually infinity, still infinity. Now, in that case, what we still have as the shortest, the minimum distance is still 1 in that, and that's still between A and B and between A and C. So there's no difference. So we just chose B, and when we walk from B, we have that from A to C through B is actually 2. So the smallest of the two, when considering A and B and A and C, is actually AC. So we go to C. Now, what happens next is that you now have an instance whereby we now have from C to D. C to D will be 1. C to D will be 2. In that, what we have is that from A to C is 1, and from C to D is 1, which gives us 2. But if you go through A to B, that's 1, B to C, that's 1, and C to D is also 1. So what we'll be able to establish at the end of the day is this. Sorry about that. Is that the shortest distance, if you look at it, but what we have really established at the end of the day is that from A to A is 0. A to B is 1, A to C is 1, and that A to D is 2. Now, but really, how do we get from A to C? A to D, rather. The connection between A to D is gotten from the connection between C and D, which is 1, and A and C, which is 1. So that's why we have the connection between A and D as 2. That's how this algorithm works. So what it basically does, it finds the shortest distance between two nodes, A to B. Okay, the connection between in A is B and C. So it finds the shortest distance. But in this case, since we do not have a short distance between, because A to C and A to B are equal, you know that but to go from A to C, there are 2 routes by which you can go from A to C. The shortest of the route is from A directly to C, which is 1. That is why B will be abandoned in that case. So you now find a situation whereby to go from A to B to C to D would give us 3. But to go from A to D will give us 2. That's really how the algorithm works. What it basically does is it finds all the distance between the beginning node, which is our source, and every other node that is connected to the node we are considering. Now, in this case, we are looking at A, between A and C. But I think it will become clearer because this is unweighted. It sometimes can be difficult, especially if I'm doing it the way we are doing it now, to explain. But let me see if there's a weighted example in this slide, because it will make it, because we are dealing with just one, sometimes it can be confusing. Yes, you might say you have gotten it because this is a simple representation, but if it comes to a complex one, it might not be so clear. But what is important to note is this. Okay, is this, that you would, when you are dealing with a particular node, you look at all the nodes that are its neighbors. Its neighbors are those nodes that are connected to it. In the case of A, it is C and B. So you will now look at between those neighbors, which is the shortest between the 2 neighbors. If they were weighted, you will look at, okay, what is the shortest distance between A and B and A and C? You will then choose that one and continue down that road. Then you go to that new point, and then you now look at that new point and say, what is the shortest distance? And look at that new point with all, let's say in that case, we could say it's C, and look at what are all the neighbors of C, and then find the shortest distance between them and go to that new point. That's, I don't know if I was able to explain that. So if you didn't really understand it, can you please kindly raise up your hand so that I'll see what I can do about that. But a weighted example would have been great for this. But I will continue if there's no question and go to the next one. In this case now, what we are dealing with here is what you're looking at now in this diagram now is the concept of importance. This is where we are dealing with things like PageRank, for example. This is basically when we are dealing with the PageRank algorithm. Now, like I said earlier on, even when you're talking about social networks, for example, there are people who have followers, especially when you are dealing with networks like, for example, Twitter, or in some cases, Instagram. Don't mind me, I'm not very good with social network. You would notice now, if you look at this diagram, obviously, if I were to ask you which nodes are the most important, you likely look at these nodes in the center, especially this one, the one in the center to the left. You would say that is more important, but looking at this, it is difficult to say that it is more important because there is no direction. Why do I say that? What if, yes, in this non-directional setting, you could say it is the most important, the one to the left. But if there was a direction, for example, and all these smaller nodes are connected to this middle one in the left, what if this one to the right, which has a smaller level of only 3 connecting to it on the right, was also this one that seems to be important on the left was also directly connected to it? For example, let's say this one to the left in terms of importance is, let's say, somebody like Lady Gaga, who has millions of followers on Instagram and on Twitter and stuff like that, and Lady Gaga was following maybe Teju, for example. Let's say Teju is this one that has these 3 people following her, but also Teju has Lady Gaga following her. Now, in reality, anybody that looks at it and say, how does Teju have Lady Gaga following her? Teju must be important if she has Lady Gaga that has maybe tens or hundreds of millions of followers following her. So direction really matters. But in this sense, looking at it non-directionally, you would say that the most important is obviously the one in the middle to the left. So this is really what it's about, because in the case of PageRank, like when Google is ranking pages, what it simply does is this: if a particular page, it goes from one page to the other, but what it's trying to see is the page that we rank the highest is the page that not only has the content you're looking for. For example, if you were searching for data science, the page that will be ranked the highest will have content on data science. But not only that, that page also will have direct links. That means a lot of other important pages, or a lot of pages on the internet that also has content of data science, are linking to it, in that they are looking at it like some kind of a source. So if you become a source to so many other pages on the same topic, or not just in terms of quantity of number of pages, but also certain other pages which also have millions of people looking at them as source, and looking at your page as also as their main source, it means that your page is very, very important in the discourse with respect to data science, and as such, your page will be ranked highest. Now, remember, what we are dealing with here is organic search. What I mean by organic search is, if you look at Google search, if you search Google, it will give you a list of search results that those are advertised, they are paid for. Google puts them there, and it basically categorizes them as ones that, so they are paid search. So they are coming up because they have paid Google to put them up there. But when it comes to organic search works by how other pages on the internet, on the World Wide Web, have described your own particular page as important. And how do they describe you as important? Is by linking to you as a source. That's simply it. So that's really what made Google blow other search engine out of the water, because there was a better way. So it ended up bringing search results that were better, because if other pages on the internet have said that, have taken this particular page as a source for their own content, and by notion they have added credibility to that source, and they have said that we find this source credible enough that we can use this as a source. It's just like citation. You know, in academic literature, when you are writing, we hear about certain write-ups that have been cited the most. What it means is that that write-up is so credible that thousands or possibly millions of people have so far not only read it, but they have thought that the content from that write-up is important enough that they can take a part of that write-up and make it a part of their own write-up, and therefore attribute credit to it. So they end up getting a lot of citations. That's really what PageRank is about. Now, the algorithm itself is really what you call a random walk algorithm, in that it repeated, remember the concept of neighbors. Now, let me just go up a bit. Now, you would see that the concept of neighbors is this. A has two neighbors, which is C and B. C has three neighbors, which is D, B, and A. D has only one neighbor, which is C. So that's the concept of neighbors. So what basically happens is that it comes onto a page and then jumps from that page to, obviously, neighbors. What creates neighbors in this sense is links, connection. Which other pages are linked to this page in terms of, are they citing it, or is this page citing that page? So that it jumps from one until, and it does it. For example, if you see the implementation we will do when we go to our Jupyter notebook, we will iterate this 1,000 times. I don't know for each particular. Obviously, when you search on Google, it possibly does it probably millions or billions of times. So it will just go randomly from a particular page to other its neighbors and seeing, oh, where is the link coming from? What is the direction? And then from that, it can come up with the level of importance of each particular page. Then it will rank it based on that importance. So far, let me pause a bit. Does anyone have a question? Okay, so far no questions yet. This is basically the mathematical part of it. So here basically is explaining to us how you do the math calculation, how you go from how you basically do it and then come up with a rank. We will implement that in the notebook when we get there. This is a lot of, but you need to understand that's why last week it was important when, when we're talking about linear algebra, a lot of this stuff will be done, is done using a lot of matrices, multiplication and stuff like that, as we will see when we go to the notebook. So this is a typical example of how this can be done. I think this is the same one we will do in the notebook example when we get there. So now, when it comes to community detection, which is where I forgot, there's the name, what's the name of that algorithm? Okay, the Girvan-Newman Algorithm, whereby we use it to find communities, especially on things like, well, it's not necessarily only with respect to social networks. It could also be used in road networks. You can have a situation whereby, for example, you could say that the island and the mainland, in terms of Lagos, those are different communities. You could look at them as communities because there are several ways you probably can go from Oshodi to maybe a certain place within the mainland. But if you want to go from the mainland to the island, there are probably only 3 or 4 ways at the most. So you could broadly categorize the mainland, which we obviously do it in Lagos. There's a dichotomy between, there's an island and there's a mainland. So we could look at them as communities, in that there are only few links between the mainland and the island, but there are much more links between the smaller communities between the mainland, but maybe not so much on the island, because the island sometimes there are very few roads also within even the island itself. So, but that's a broad example you could use. Now, so what it's trying to see is you're trying to look at scenarios whereby you have very dense connection between certain finite amount of nodes, where they are much more connected to themselves than with other nodes within the graph. Like the example we can see here, you can see obviously that there seems to be 3 communities here. One to the right, one to the left, and one at the bottom middle. So this is, like they said, this is fundamental to social network. Remember, for example, on LinkedIn, there are things we call on LinkedIn, you have on your connection, there are people that are on the, I think it's first degree, second degree, and third degree. What it basically means is your first degree means connection are possibly people you are directly connected to. Then I think your second degree is people who are connected to people you are connected to. While the third degree is, as the case may be, and going. So these are very, very applicable to the workings of social media. So they are pretty important, especially in the times we live in, whereby the world has become very connected on social media. Now, another important thing that will come up here is, which is why I think it was important that sometimes to be able to understand this thing, the only reason I have a good understanding of these things to an extent is because I had consumed content on data structure and algorithms before even getting. It was actually when I was reading the book, I got to a place whereby they were now dealing with graphs and some algorithms that could be used on graphs. Breadth first algorithm, then the the algorithm we dealt with earlier on, that I now even remember that the class for this week is actually supposed to be on graph, and I now had to go on. But for some reason now, some people might not understand what they say the basic idea is recursively partitioning the network by removing edges. Recursion is a very, very important concept when you're an concept, an idea where you're dealing with data structures and algorithm. Recursion is basically a way of, I think one of the easiest way of doing it is, I can explain it, is when you are implementing a factorial. I think that's the easiest way. You will notice that 9 factorial is just 9 times 8 factorial. And 9 factorial is also 9 times, is it times or plus? Somebody correct me if I'm wrong. I think 9 factorial is also 9 times 8 times 7 factorial. 9 factorial is also still 9 times 8 times 7 times 6 factorial. So basically, a factorial is a multiplication of itself times every other value that is associated, that is less than it. So 9 factorial is just 9 times 8 times 7 till 1. That's what 9 factorial is. So that is a recursive process. What it means is that as you have 9 factorial will also, if you want to be able to calculate, like if you want to run, if you want to probably declare a function that helps you calculate the factorial of a number, the easiest way to do it is to use recursion. The only condition you would give it is with respect to, I think, to, because 2 factorial is 2 times 1, which is 2. Now, 1 factorial is simply 1. I think you first take care of the first 2 instances, but only 0 and 1 is what you consider. Then you will tell it to do the same thing over and over again. Like we said, 9 factorial is simply 9 times 8 factorial. So 8 factorial will simply be 8 times. So it will just pull 9. Your function will basically pull 9, then call itself again. That function will call itself again. So it will do a factorial. So you say, let's say factorial of 9. If you give it a variable 9, an argument 9. So what it will do is, it will take the first value, what the variable you gave it, and keep it and say multiply it to be 9 times 8 factorial. Then it will continue. So you know that 8 factorial will now be 8 times 7 factorial. It will continue until you get to 1, 1.
Please, let's hold on for a while. Let me try and reach out to him. In the meantime, Tej, is there anything you want to tell the tell everyone?
Sorry guys, I got disconnected. Sorry about that. Let me get back to it. Okay. So the algorithm basically it's like loops through and disconnects certain edges. Now let's try and look at it, because one of the things I try to do is try to understand, make common sense of what the algorithm is trying to do. It helps me because if I can't do that in my head, I wouldn't understand the maths. I wouldn't even bother, because that's how I function. If I can't understand it, going to the maths just doesn't make any sense for me. So now look at it this way. If you were trying to look at what we have on the screen now, if you were trying to disconnect, if you were trying to find out which are the communities that are more connected than other, and you start randomly disconnecting, cutting off particular edges. Let's say you cut off a particular edge and you find out that you can still get to certain groups or certain nodes conveniently. There are still so many other ways by which you can get to all those nodes. And even if you disconnect one, or you keep disconnecting different one at a time, it shows you that those nodes are tightly connected. But if you disconnect a particular edge and you find out that getting to particular groups of nodes become increasingly difficult, maybe, for example, if you I use the example of the mainland and the island because it's the easiest one to use. If you remove Third Mainland Bridge, all of us that work on the island, that live on the mainland, we're in serious trouble. We're in serious trouble. Look at, I think they closed down one of the 3 bridges that lead from the mainland to the island for repairs, because they said there were some issues and they wanted to, I think it's the Echo Bridge. What that meant is we now had only 2 access to the island. So it will increase the level of traffic on those 2 other bridges as they go to the island. It shows you that the island and the mainland are tightly connected. They are communities on their own, or much larger communities for that matter. So think about it that way. So if you remove one edge, what effect does it have on other nodes around it? That's what the algorithm is trying to find out. So to the extent that having to remove a particular edge means that a particular group of communities still can access each other, but they can't really access another group, means that those are communities. That's really what this algorithm tries to do. So that's what this algorithm tries to do. So this is an illustration. If you look at this now, you have different nodes. I think nodes from 1 to 14, and you have different edges. Let's just look at this. If you see this now, the moment we removed this node between 7 and 8, you will notice that there's no connection between the right-hand side and the left-hand side. So it shows you that these are communities. But also you can also see that there are also sub-communities within these 2 communities. So if you removed, again, you can see that we now have 4 sub-communities. So you could see that 7 and 8 are actually very, very important nodes that are holding these communities together. that are pulling them within the network. But really, all these three, 1, 2, 3, 4, 5, 6, nine, 10, 11 within the network. Sorry guys, can you still hear me? Okay.
Yes, we can.
All right. So it shows you that because it's a network, there are people who obviously might not necessarily be in these individual communities, but they are connected to certain members of the communities. So they become like the link that makes the network complete. But in a sense, if you can remove those edges, you can easily find the communities, the different communities. You could also look at them as segments, like I said. Remember, a community basically looks at people with, a community is made up of people with maybe certain characteristics. It could be race, it could be color, it could be profession, it could be any other thing, it could be interest. So you could easily find these interest groups, these communities within a network. So that's what that algorithm basically does. But what eventually happens is that the representation is such that, remember, it forms something we call a dendrogram. Now, a dendrogram is a basic hierarchy. So if you look at this dendrogram now, you see that the 1, 2, 3 are, although the 4 different communities we have and the 2 individuals, which are 7 and 8, are within the same level. But you see that each community is connected together. So at the second level, 1, 2, 3 are connected together. 4, 5, 6 are connected to each other. 9, 10, 11 are connected to each other, and 12, 13, 14 are connected. But at the second level, at the third level, you'll now find out that this community of 9, 10, 11 are connected to the community of 12, 13, 14. And there's also an individual node, it could be an individual of 8, that is all
While we wait for IK to rejoin us, any questions so far? Kindly raise your hand if you'd like to say something. Are we all clear with the explanation? Do we all agree with why we need to understand graphs and some of these interesting graph algorithms? Okay, still no hands raised. Oh, okay. ASS the Lagos would like to speak. Kenichi, the raising of hand does not, you're excluded. Go ahead.
Okay, guys, please ask questions now. I'm begging you guys. Do we all understand? Although I'm not the one who answered the question, it's Ike that answered the question. Okay, Victor. Victor, you want to ask a question? Okay. In the meantime, can I? Okay. Obiora wants to say something. You can speak. Yeah.
Okay, so since we are looking for question now, I was thinking of the poll. So the slide had polls there, and I hoped we could just go back to the polls and then look at what the correct answer should be.
Okay. For the polls, yeah?
Yeah.
Okay, I'll inform Ike once it comes in, because I'm not sure I was around when that poll was shown. Okay, Ike is here, thank God, just at the right time. Ike.
Which of the polls are you referring to?
Okay, head us, thank God.
Is it this one?
So
go ahead.
Actually, the first one, anyone, the first one, I think actually mean the first one. The first one is okay for me, but we can look at the other polls.
This one.
Sorry.
Okay,
yes,
this is the.
yes,
I think this is the first
is this
poll.
the first one? Yeah.
Okay, hold on. Let me see if there is another poll. I think that's it.
Yes, this is it. This is it.
Now, so the idea behind we don't have a system set up, because the idea behind the polling is that the students are actually supposed to be the ones to answer. So the floor is open. Any student, any of us can answer this particular question. So who has some kind of an answer? Please help us.
So we could do something, right? Within the next 3 minutes, maybe that's too long, you can decide. Everyone should give an answer and just write it, put it on the chart, and then you go ahead to give the correct answer, and we can sort of like see. Don't think you know, you don't want people to see that you didn't know this or something. This is learning curve, and so don't bother. Just put in what you feel should be the answer, and if it's not correct, then you've learned something. If it's correct, then yeah, you've reinforced your learning. IK, does that make sense?
Yes, it does. So let's just try and answer it. I think we can use the comments, our chat, and just drop our own answer. What do we think? Then we can look at what the right answer is. Please, you are free to get it wrong. Don't be scared of getting it wrong. That's allowed.
So I'm going to be the timer. Poll closes in 1 minute. Okay, I would add 1 more minute.
You can answer this question, bro. I know.
Okay, that's the end of the poll. So we only had about, I think, 5 people participated, and the highest votes for it, I was counting. So the highest votes are option 2 and 5. So okay, so now the highest vote is option 5 actually. So we have 2, 5, 3, and 6 or thereabouts. So you can go ahead with the class, Kenichi, to maybe give the answer or something.
Okay. Um, for now, can for now I can't come up with an answer, specific answers for it for now. I don't know.
Oh, okay, sorry. I just wanted to note that this poll was given in class. This is Professor Cota's slides, and he mentioned in the class, and everyone who watched the video should be able to see the answers because it was like it's all in the class videos. So if I can just go back to what, not I'm not talking to IK in particular, I'm talking to everyone in the class. Just go back to watch the video and you can see the answer. Maybe you're right or you're wrong. Okay, can continue with the class. Okay, I'm not sure if we lost IK or something, so let's read the question together. Suppose we have a directed graph with n nodes. We all know what a directed graph is right now. It means that if you, let's say the nodes that you have are 3, A, B, C. A is connected to B and B is connected to C. In a directed graph, it means that A connects to B, does not, like B does not connect to, imagine an arrow. So you have an arrow that just leads A to B. So if the arrow is facing B, it means that A can only move from A to B. B can't move from B back to A. I hope you can get the mental picture. So where each node has fewer than some constant K. Okay, I lost this slide. Pardon me, I don't have the slide on my laptop because I wasn't planning to give a lecture. Okay, it's back. Okay. Okay. Anyway, so constant timing, like if you think about, so there's a question, how if you if you're just moving from one part to another, how should I explain this? So if you want to delete something, you just say pick out of, you have let's say you have an array, and delete operation is usually like you just, oh god, this is harder to explain without writing something down or something, or having a much more prepared slide to show you. But most of these things are discussed in the lecture video much more. But option one, which is checking if there is a link between two nodes. If you want to check, maybe you do a for loop. You say for all the links that are here, does A connect to B? Is that a constant time? Finding all outgoing edges. So you have to understand something about like constant time, logarithmic time, and basically you have some understanding of big O notation. And I can't explain it in a simpler terms right now because I'm not prepared to explain it. But if we still
Alexa, someone is raising up his hand.
If you raised up your hand, okay, Olawale, please go ahead to speak.
Yeah, sorry, I was just going to say, because for the option one, for direct relationship between nodes A and B, I think it depends on how it's, sorry, I'm looking for the word. Okay, so the thing is, I've worked with a GraphDB before, Neo4j, and it's pretty easy to just check if there's a relationship between two nodes. So I don't know how it's implemented behind, but like from what you said about for loop, I'm not exactly sure if that's how it works. I think it's more like select statements in SQL where it's ingrained somehow, or like indexes basically. So it's quite fast, and the operation shouldn't increase with time. I can research into that just to be sure, but that was the opinion I had, and that's what I wanted to say.
No, thanks for that. I wasn't insinuating that checking if there is a link between two nodes A and B is not a constant time. I have to go back to confirm this as well. I was just trying to explain from what I understand with inserting, deleting. I know that if I'm not wrong, deleting is either constant time. I think it's constant time. It's just I'm not sure. So that's why I don't want to give false information. I have to go back to check this thing out. It's been a while. If anyone have much more, did anyone see the video? You might have a much more updated answer than any of us. Okay, Kende, please go ahead to speak.
Okay. Okay. Kende, go ahead.
Sorry, I made a mistake. I didn't intentionally raise up my hand. I can continue. Sorry for the
Obiora, do you have something to say? Go ahead, please.
Okay, so I think checking if that's the number one option there, checking if there's a link between two nodes, it's constant time. Why do I think so? It's because it's stored in the dictionary, and you can just access the first node as the key of the dictionary, and right away in constant time it tells you the outgoing nodes from A. So as if you put A as a key, it tells you the outgoing nodes, because those are the values that are fixed to that key. And you can do the same thing for B. if you want to know, okay, A links to B, does B link to A, you still use B again as the key to that dictionary. And so dictionary checks, as in using keys, is actually constant time. So that's why I think number one is constant time. Then for number two, finding all outgoing nodes, outgoing edges of a node A. So I also think that's constant time because in fact that's the whole essence of the adjacency dictionary or something like that. What it's called. It's the outgoing nodes that are stored as values to a particular key. The key will be A and the outgoing nodes will be the values appended to that key in the dictionary. So, and dictionary checks are constant time. Please, if I'm wrong, you can correct me. Thank you very much.
No, actually, Obiora, it's like you just joggled my memory. You're extreme, like you're very correct. Dictionary timer, if you're checking it's constant time. I just remember that deleting is not constant because it's you have to find all the, for example, the keys. Let's say A is a key, then it has you have the value as an array of all the nodes that A is connected to. You get? So if you need to delete a node that A is connected to, you need to first get to A, then find the connection, then delete it. So it becomes, it's not a constant time anymore. So
exactly.
I would say that number 5 is not correct. So let's think about like finding all incoming edges of a node A. Is that constant time from the definition that we've defined now? Like Obiora already helped us with the premises, which is you store all your graphs as a dictionary. So if you wanted to find all the incoming edges of a node, would that still be constant time? Could you just get it? I have to think a little bit about that.
Okay,
Sorry.
so I don't think, okay, so on this side, okay, so Teju, on this side, I first of all, the poll wasn't included in the video. I know you referred us back to the video. It seems as if one of the videos is actually missing. From 6, it jumped to 8 or something like that. But looking at that number 5, the deleting the link between two nodes. Okay, if we have node A, we want to delete the link between A and B. We can just use the dictionary to access the values that are connected to A, that A links to, and then remove it from that dictionary because it's like a dictionary of dictionaries, something like that, Sha. Then the B, we can also use the second node B that will access B and then delete any link it has to A. So I think it still goes on to constant time.
When you said you get to the dictionary, then I mean, of course, I might be totally wrong about this. I'm happy to come back to correct myself. But what you said you move from, like, you get the A, then you find whatever node it is, then you delete, right?
Yes, if B is part of what it links to.
That is not constant anymore. It's like you're doing more than one operation. Constant time means you're doing just one operation. You just do this. If I'm wrong, if someone is good in algorithm, like if you're an algorithm ninja, please feel free to correct any one of us. But as per the poll and the video, I would and I'll come back to the class again, maybe on Slack or something. I'll look at it after, just to discuss better.
Yeah, we have someone raising up his hand. Chizu wants to say something.
Hello. Go ahead.
So I was thinking, if you go ahead, like if you go back to the previous page before the poll,
okay,
listed under the pros of the
yeah.
adjacent dictionary, it says easy to add.
Right, A, B. I think this is like we can use this as a yeah, exactly.
Yeah, easy to add, remove, and query edges. So if you are following that, I would say number 2, number 3, and number 4 would be order 1 constant time complexity. Then probably, as from like what the previous person was saying, deleting a link, and I think also adding a new node would be in linear time complexity. So I guess the only one I'm not sure of is
Already written
number
here
1.
actually, so that means I am very wrong. So it's here that the pros is that he said if you're using the adjacency dictionary, and then it's easy to add, remove, and query edges. But the only
Yeah.
problem is that it has an overhead of using a dictionary. I think I was talking about the array parts. Can you go back one slide as well? So here, yeah, exactly. I was thinking, I mentioned that if your key is A, B, or like whatever, then if your value is an array of other nodes, I think I mentioned that. I wasn't thinking about your value being a dictionary of like a dictionary of key value again. So I think that was where the misconception from my part is. Apologies for the if it looks like it was misleading. So for arrays, it says here that if you have a key value of this, then it's easy to get all the outgoing links from a given node. If you look at it, A is connected to B, B is connected to C. These are what linked graph, right? What's the right terminology, please?
Or
Directional, rather. So these
okay,
are
yeah, direct.
directional graph. So, and C is connected to A and D. So if you have this, if you're trying to represent your graph in this fashion, then it's easy to get all the outgoing links from a given node. You can if you still don't understand that, we can go in depth after class, but this looks very this looks visual, but it's okay if you can visualize it as much as I was thinking. Then it says that it is fast to add new nodes. These are just these are attributes of arrays. Like you can just do a dot append. If you're familiar with the normal Python stuff, imagine you have an array that, let's say 1 to 3, and you want to append 4. All you do is just do this list dot append. So that's why it's easy to add or to to add some new links to it and everything. But if you wanted to delete an edge from it, then it becomes really difficult because you have to scan through. You have to do for every element. If this element equals to this, then delete. Does that make sense to you? So if you have an array and you need to delete, let's say you have an array of A, B, C, D, E, and I want to delete E, I can't just say look up E. No, it's non-existent. I have to say for every element in this array, if you find E, then remove E from this array. Does that make sense to you?
Yes, it
So
does.
that makes it difficult. That makes it difficult for you to remove any edge. But if you go back to slide 12 and you represent your graph as an adjacency dictionary, then you can do the same thing as you're doing. It becomes like a lookup table. But then, like it says, the overhead here is that now you have dictionary of dictionary. So it becomes like maybe not necessarily a huge overhead, but it's faster to look up. Another thing some people do is you can also kind of like have each of the, so not if you have a list, you can have what's the word, index of the list. So if you know the index, if you know that there is E and you know where it is, maybe it's index 7, then you can just do it like a lookup. Then that becomes it's like you're keeping a track of the index and the list itself. That's also I don't know. That's also one option if you I haven't tried much of that. So that's my 2 cents. I don't know if I was being clear enough, and apologies for the back and forth. I totally was not prepared for answering any questions, so pardon me.
Okay, all right, guys. I think at this point, I think there's a second goal. Let me see. I hope that one is not also too complex. Okay. Yeah.
So Kelechi just
go to
reached
the
out
code.
privately that we don't have much time because
right.
the next class is supposed to start.
Okay. I think what we can do now is just we can go over to the although what you find in the notebook, what you find in the notebook is also mostly what's on the slide. So, but let's just look at the notebook, run a bit of the code, then the rest of it, whatever we can do between now and the next 10-15 minutes, then we can, so that we can make room for people in the next class. Let me just quickly.
Okay. So while you do that, I just want to say that thank you for bringing attention to the poll. I think this is a very good point for discussion. So we can take it to Slack, and all the other polls, then we can discuss on Slack, if that makes sense to everyone. I think that would be a lot more interactive, and we can explain stuff to ourselves over Slack.
Okay. Now to the notebook. Now, basically, there are only two things really that this notebook is just basically working with arrays, just like what we did last week. Then we would ask that you work with. There's a library for working with graphs in Python, which is discussed later in the notebook. But let's see if we can get to that. Okay, so this is basically what we have. The notebook basically explains all that we've gone through in the slides, going through graph models, directed and weighted and unweighted, with all the implementations. Now, but I think there's a point. This is the first. Okay, here what is being explained is he basically just puts this was also in the slide, he puts the all nodes within a set and a tuple of the a set of the edges also that we also saw in the slide. This is an explanation of what the adjacency list is, and implementation of it using list. Basically, you just put all the nodes within a list. Then in that case, what you do is you basically have each individual nodes. So you know that there's A, B, C, and D. Then there's an implementation of the adjacency dictionary, where we try to really, what we're trying to do here is to reproduce this. But in this case, what we are doing is we are using the index. In this case, we are using the index of the individual nodes as, let's say, their weights in this case, because that's really what happens when you do, when we enumerate each of the nodes. So we have 4 different nodes. We enumerate it in, so, and we just create a dictionary of the value and the index. That's what this dictionary comprehension here. Basically, what we are saying is for index value in enumerate nodes, give us the value index, which is what we eventually reproduce here. Now, remember what we were saying earlier on, that if we wanted to do this using the, I know I had this when I was trying to explain the adjacency list. If you wanted to show the weight, you would have to put it in a different list. So unlike what we did here earlier on, where we put the nodes in a list, we can also come down here and then represent the weight of nodes with a list of its own, basically making it possible that, remember, like we said, so like you see, the adjacency with 0 is 1, which means that node 0, A, has a link to B, while link B has a link to node 2, which is C. Then C has a link to 2 other nodes, which is 0 being A, and node 3 being D. So while D has a link to none. That's what is basically shown here. Then in dealing with adjacency dictionaries, basically we've implemented a dictionary of dictionaries, whereby the key of the initial dictionary is the node, while the value, which is a dictionary itself, contains the edge and also the weight. So what we have here now is we notice that in this dictionary, we have A that is connected to B and the weight is 1. We have B connected to C, the weight is 1, C connected to D, A, the weight as 1, C connected to D, the weight as 1, while D is connected to nothing. So these are just the basic implementations of all this. Let me just keep running them. Now, in the adjacency metrics, remember what we tried to do is represent the nodes and and the edges and the magnitude within a square matrix, where we have the nodes both as columns and as rows. So we ended up having something like this. So we could easily implement that using this. But in that case, this notebook also goes ahead to help us implement. Yes, we dealt with 3 algorithms, but in this notebook, the implementation done here is that of the PageRank algorithm. Remember, there was this mathematical formula over here, or the process which, remember, it's an iterative process in that it looks at importance. We calculate the importance of a particular node based on the fact that it jumps from one link to the other. I remember I told you that this is the implementation of it down here using NumPy, really. So what we basically do is we create a square matrix, a 4x4 matrix. Then we specify certain values. In this case, let's just go up and look at the values. We specify our D value and our T value, where D being our probability and T being our count. Now, what we mean by the probability is when you jump from one page to another, you want to calculate the probability that this one page is connected to another. Then the count is eventually, when you count all the links on the page, you use them in this formula to derive the importance of each page at the end of it, to know what is more important than the other. So when you run through all this, you come up with, remember we're dealing with 4 different nodes. You come up with a level of importance of the nodes. In this case, you see that node C is obviously more important because there is more connection. There's more connected to our node C of the 4 nodes we've been dealing with, of these 4. So C connects to A and C connects to D. But every other one connects to 1 while D doesn't connect. So ordinarily, D should have the lowest level of importance if we look down here. But is that the case? Okay. I think both D and A have the same level of importance, but obviously B and C were much more important. But as you can see, C is more important in that, remember, when we're dealing with PageRank, we're looking at the page that has more connected to it. In that it's seen by others as being more valuable and more important. But okay, so this is the basic implementation of the PageRank algorithm on using NumPy. Obviously, based on last week's class, we should be able to understand most of what is happening here. If you don't understand it, my advice would be do something like this. Break it down into the individual components so that you can understand, okay, what's happening here. We made a copy. Okay, what happens here? What happens on the individual line? Run it individually on new tabs, new cells, so that you can know what is happening in each individual stage. Then here, this is the point where we run it. We do the iteration 1,000 times, where range T being range 1,000, and then we come up with a value of which is more important based on that iteration. Now we have another class in like about 4 minutes. There's an implementation of this is the package, the network S graph library in Python is used to implement, is used for dealing with graphs in Python. What I would advise we do is, let's look at this during the, especially this weekend, look at it, then whatever issues you come up with, you can just basically on Slack reach out to us so that we can have some kind of a discussion. Obviously, we're also putting up the poll on Slack so that there can be some kind of interaction on Slack. So I wouldn't want to go to the details of this library because there's a lot to cover here, and 4 minutes might not be enough to do that. So just look at it. Then if ask questions on Slack, you can reach out to individuals on Slack and ask particular question if and when you have them. Then we'll just take it from there. So that conversation will be left for us to have on Slack on the various implementation of graphs. What you could do also is to find simple, because if you were to go to use a particular library, you want to use it for something. So another way you could use this is to find how, okay, you could easily go through this to implement the 3 different algorithms using this library. That's a way. Or you could find small smaller implementations of and usage of graph for doing something in the Python language, then try to do it on using this library. And as you have questions, just throw them on Slack and we'll take it from there. I believe that's really what we have for today. Kene, I don't know if you have any other information.
Okay, guys. Sorry, I was off and on in the class, but I noticed that there was a bit of issue with graphs. So unfortunately, I didn't go through the materials to see. I wasn't following you guys, so I didn't even know where the issues were coming from. But let me share my screen. There's something I remember that when myself and Teju were taking the class. Okay. When myself and Teju were taking the class that was last year, yeah. I remember Teju implemented graphs from scratch. So while you guys were discussing, I was actually looking for where we kept those codes here. So can you guys see my screen now?
Yes.
Okay.
Yes, we can.
That feels like a long time ago, Kenny.
That the stuff of it, yeah. So what everyone can do here, I'll look at it again and try and remember what we're trying to do here. But what we did is this.
You are trying to remember what we did. Wow.
Okay. So we implemented this Dijkstra. I don't know how to pronounce his name. I never knew how to pronounce his name. Dijkstra, yeah. We implemented this, yeah, and also the PageRank algorithm from scratch. But what we did also was that after implementing each of them, we compared the results with network X. Yeah, so I can't really remember what happened here, right? But this is the result from the from scratch algorithm Teju root. And this is the result from network X here. Then for the PageRank, you'll notice something, yeah? You'll notice that this is the result we got from the from scratch method. And then from the network X, this is the result we have. But for this particular one, if you can check, you'll find out that there's a kind of similarity between what the from scratch has and then what network X has, right? So you see it has similar values, although this one truncated at some points, yeah? So I believe that if we all can go through these codes, yeah, we'll be able to have a clear understanding of how this network works. I would also do it, I would also look at it, and then I'm available to answer questions on Slack as usual.
So you share this, right?
Yes, so I'm supposed to put it on I'll put it on, where is, okay. Trying to chat here.
Yeah, I remember I had a lot of fun with this particular chat.
Okay, cool.
That's...
I've posted, the links are, I've sent the links out here. So I have 2 minutes more. And in this 2 minutes, I want to discuss something. Okay, can you see my screen now?
Yes, we can.
Okay, so can you see the curriculum? Can you all see the curriculum?
No.
It's not the curriculum, yeah?
You're still showing the notebook.
Okay, so let me switch to the curriculum. Okay, can you see the curriculum now?
Yes, please.
Yes,
okay.
we can.
So you all notice that there's a big break here. So by the time, it invariably means that by the time we finish this class here, we'll be going into what machine learning is basically. That's we're leaving that phase of learning Python, doing some data analysis and some other things. Yeah. And then we are moving into Python and moving into machine learning. And I want to employ everyone that if you've not really been putting too much effort before, I think you should put in efforts now, because trust me. And then if you have questions that are answered in the previous classes, try and clear them off before we move into machine learning, because machine learning is something that if you miss it, or if you miss one concept, right, it might scatter everything, even to the end, yeah? So, but please, just try as much as possible to familiarize with yourself with everything here, most especially this, the lecture 1, 2, 3, 4, most especially, and then maybe lecture 6. For graphs and networks, for now, you might not really, yes, there's an it's important here, but for now, I don't think it's something that you should base all your efforts on, right? The most important things for now are week 1, week 2, week 3, week 4, and week 6. And then I'll talk about week 6 here. So week 6 is free text and natural language processing. And as usual, everyone is supposed to go through the materials before the class on Saturday. And just to bring in some interesting stuff, yeah, I already gave you guys some practice last week, of which I think only 4 people were able to attempt. And I hope they enjoyed themselves. For those who didn't attempt it, I hope you still learned about matrices well. Yeah. So, but for this natural language processing, yeah, and free text, yeah, what you're going to be doing basically is learning how to pre-process natural languages. Yeah, I won't go into details of what it entails. You go through the materials. But what I want to say is this: that sometime within the week, maybe on Tuesday or Wednesday, I'll be sending out a practice as usual. And let me share my screen to see. Let me change my screen to where it is so that you see what I'm trying to say. How many of us know about sentiment prediction? You just raise your hands. Don't just show by raising up your hands. Or how many of you have heard of sentiment prediction? Okay. So how many of us can implement it? Okay. So now the hands are reducing. How many can implement it? If you can implement it, raise your hand. Oh, the hands are still reducing. Remaining 2. Okay, so Chidima and Oris, you can implement it. And Oris, Michael. We have gurus here. One hand has gone up. You can implement it from scratch, not with the library. Oh, the hands are reducing again. Yeah, that's fine. Oh, no hands again. Oh, that's beautiful.
Even if you can implement it library, do you want to eat scratch?
Okay. but you know, you guys, it's important to understand what happens behind the scene. When you become the boss, yeah, you can use any library. Doesn't matter, but you understand what is happening. Okay, so you guys can see my screen, yeah? So can you guys see my screen? Can you see step 1, create a data set?
Yes.
Okay. So basically, what it's going to be is this. This notebook, I used it for the last cohort 3. And then what we did was this. Everything that was learned in the class here was implemented in pre-processing the data for sentiment prediction, right? So if you don't understand, if you don't go through the class, the free text and natural language processing class, you might not be able to implement what is here. So now what I want you guys to do is this. Go through the class, go through the videos, go through the slides. And when you're done with the slides, and then after I have released this, I'll make this more or less like a fill in the gap stuff, yeah? You'll be able to implement this. And if you're able to implement it correctly, somewhere towards the end, you don't need to bother yourself about the code, right? You don't need to bother yourself about the code by the implement that trains the model to do the sentiment prediction. That has been done already. But by the time you're done with the pre-processing, if you pass your pre-processed data inside this function that I have written here, already I've written the codes inside this sentiment network. By the time you pass in your pre-processed data here, your model should train. So you would see something like this. And if it trains, it will be able to predict better, your sentiment. So you can see here that Kenichi is a very good something, and it says it's a positive sentiment here. And then you'd see here that I did some other better models and all that. So the idea is this: go through the slides and videos, try and implement the pre-processing stage, and then see how well your model trains based on the data you have pre-processed. Is that fine by everyone? Just raise your hand. If you don't understand, you can chat me up on Slack because we are out of time. We are 5 minutes above our time. Okay, so no one understands what I was saying. Okay, 14. Okay, so I would assume everybody understands. Obiora understands. So if you don't know anything about sentiment networks or sentiment analysis, please go and read about sentiment analysis. Yeah, I'm not going to teach you what sentiment analysis is. You should learn how to read things on your own. Okay, so that brings us to the end of the class today. As usual, we have Slack, we have emails. Communicate with us when you have issues, and make use of Slack for collaboration. Thank you, guys. You can unmute now.
Thank you.
Thank you.
Thank you.
Yeah.
Bye.
Thank you.
Thank you.
Thank you. Bye.
Yeah, thanks. Bye.
Thank you. Bye.
Hi, thank you.